Today is the last lecture of neural engineering, and I've been talking about artificial neural networks, and I hope you are a little bit familiar with the way we implement the artificial neural networks using MATLAB. And today I want to implement more the actual applications to recognize handwriting numbers. Nowadays, when you use tablet, smartphone, sometimes you jot down and then the system recognize your handwritings. Probably they're using the very similar concepts of artificial neural networks, although they use more advanced algorithms. So today we are going to build our ANS model to recognize handwriting numbers. In order to do that, we need training sets. So we are going to use the mnist data sets. If you Google mnist, then you can find many predefined data sets. Actually, in here they provide people's handwriting, especially for numbers. They provide 60,000 training sets and 10,000 test sets. I already downloaded and then uploaded on the Blackboard. Each training set consists of 785 columnar data. If you look at the one number and you digitize them, one number actually has a 28 pixel. So that's the way they scanned their handwritings. And then each pixel has information about the gray scale color. So in the computer, the 0 represent the black and 255 represent the whites. So each pixel just has any number between 0 and 255 depending on the lightness of the gray scale. One row has 28 pixels. The next one has a 28 pixel. So we have 28 pixels. So total we have 784 pixels. So each training set contains 784 pixels plus your first column contains the number indications. So if you open up training sets, the training set shows lots of number. Your first column is, let's say, 4, and then from second column through 785 column, you see each pixel's grayscale, maybe 1 or 2, 255, 178, 0. So it has each pixel's grayscale because, as I said, the first row has a 28 pixel, the second row has a 28 pixel, so that's why you have total 784 pixel data. The very first column indicates the number indications, and then we have 60,000 training sets. So how we implement this one into the ANS? The idea is this one, because each number has associated with 784 grayscale informations. We want to give 784 those grayscale information into the input node of your neural network system. And then this is our predefined 784 inputs. Your output should be either 0 or 1 or 3, so any number between 0 and 9. But since we are going to make ANN structure, rather than making only one output node for our outputs, we try to make a 10 output node like that, so that if the output is 0, then let's say we can just make 1 0 0 0 0 0 0 0 0 0. We define our 10 output node such that 1 and everything else is 0 is 1 0, and when 1 is expected, the output is like 0 1 0 0 0, like that. And when 2 is our output, then your output looks like this one. So you can put the only one for the node of your each specific node, depending on what should be your desired output. So when your output is 9, your output looks like the 1 at the end. Other node should be all zeros. Okay. So in a case, we match the 1 number output with 10 output node. That's kind of basic ideas. And then right now our input node has a 784 node. It's a lot. So what's the number of hidden node? So right now number of hidden node, in general it's better to have larger number than the input node, but this is too many. So you can maybe start 1000, but you set your hidden node as 1000, your computation time is takes too long. So for this purpose, maybe we can put this one like maybe 100. We can start with the 100, and maybe you can a little bit increase later. Once you confirm that your code is working, then you can just try to increase your node and just wait until the computation is over. Then you can test the accuracy of your success rate. So let's do the MATLAB first example here, because right now we want to first load their data sets and then structuralize our input and output, then try to train our neural networks. So let's go to the MATLAB. The very first one is that we have to load their data, right? Please make sure that your working directory, so you set your working directory under which you save the training data set. Okay, so in my computer I saved the training data set under this data and code folder. That's why my working directory is here. And then I want to read matrix function, and then the file name is mnist train 60,000, okay, and CSV file. That's the file. So I just read everything as a matrix and dumped into a df variable. Then let me save this one, ANN and mnist. I just save it like that. And then if I just run it, now it's just reading the file. The file is kind of huge, that's why it takes a little bit time. And then I see that I have an df variable, and this variable is 60 rows and 785 number. So if I just looking at my df, only the first row, then I have this many number. Okay, so my very first row has the information about the number of 5. This is my number indications. From second to the rest of them are all the pixels are grayscale information. Okay, so some of them are black, some of them white, and so on, as a horizontal formats. So since from the second column to the end is my 784 pixels data, I want to separate my x and output. So in here, my x input should be x ni, okay, is equal to df and all rows, and from 2 to end. That should be 708 pixels grayscale. Then y is equal to, my y should be or the number indications, right? That should be located in my very first column. So this one is all the rows and first column. So this one should be my number indication. And then, as I told you that I want to make all the number indications matched to the 10 output value, either 0 or 1. So in this code, I want to first make all the zeros, and then the zeros, what's the total number of training set? 60,000. Okay, but instead of writing down the 60,000 here, I just put my length is y and 10. I want to make 10 by 60,000 zeros right now for my desired output, training outputs. Then depending on my number indications, I want to put the 1 into proper locations. So that's why I can just use the for loop. So for loop 1 is 1 to length of y. Okay, and then into the zeros column, I and plus 1 is equal to 1.0 and end. So basically I just repeat 60,000 times. In my zeros column, if the I is the very first one, then my first column, for example, this is my y1, then my number indication is 5, right? So that's why I want to put the 1 into the sixes of this column. So this is, when I put the 1 on very first one, it should be 0. So when I in order to indicate number 5, I need to insert 1 into sixes the node of this one. That's why in this here, I put my y value, okay, plus 1. So whenever I change the number of training sets, I just insert 1 into this order of the node. So y1 is 5, that's why 5 plus 1 is 6. So my first and sixth node should be filled with a 1. So in any case, I can just make the y. So let me just run this one and then see. Length, there's typo. So right now, if you just looking at the y and nk, okay, so these are y and k. So y and k has 60,000 row and 10 column. So my very first number was 5. That's why I put the 1 at here. And then the second row number was 0. That's why we put the 1 on here. And third one is number 4. That's why we put the 1 on fifth here. So we just prepare all the y desired output with 1 or zeros, okay, up to 60,000 data points. So now we kind of prepared x input and y input like that. And after that, let's decide what is the number of hidden layer and so on. So hidden layer, maybe we can start from 100. You can increase later. And your output layer number is 10. We know that, but we can just use the size function, because we already created a y and k. So if you get the size number with 2, then the n output layer should be 10, and then input layer number. So we know that that's just 784, but we can just use a size function. So that should be 784. And then training set number. Now we know that this is a 60,000, okay? But let me just use the size to get the size from your input x, okay? Then after that, we set our error. Our error is learning rates. So this is 0.1. We just say 0.1 here. And after that, we have to initialize the weight, right? So let's initialize. So I want to, because we have only one hidden layer right now, so your first, the weights for the first layer, we want to make a randomized weight, right? We want to make a randomized weight. And when you randomize your weights, it's recommended that you just choose the weights from your standard normal distribution. So let's use the rand d, so we can get the value from standard normal distributions, and input layer and hidden layer. Okay. And after that, we try to divide this one is square root of the number of input layer node. And the second weights, we just try to get random number from standard normal distributions and hidden layer and output layer number. Weights ij should be 784 by 100, and the second weights is 100 by 10, and we divide all the random number by square root of number of your hidden layer. So this is kind of recommended way to set our weights. And after that, we use for loop to train your data. So right now, let's say I want to repeat 100 and everything. Then we can bring the code that we used from last lecture. Okay, so let me just copy and paste it from the last lecture. So I just copy and paste from the last lecture. This is your input and first layer, so we multiply to get the z and sigmoidal function, and then this is output from your hidden node, and then you multiply your output node with the second layer weights, and that's the z3, that we get the output from your sigmoidal, that should be your output. Then we try to get the error between your desired and your output here. Then we try to get the error. Then we try to get the delta. You mean the lambda, I mean. The last time I used the lambda instead of delta. Lambda is what we used so far, so let's put the lambda here, so we don't get confused about about that. Lambda, okay, and this is our partial derivatives, and we just weight everything. But in here, let me try to change a little bit here. When you get the error, okay, when you get the error, delete this one right now. So if you try to get the error, so error is just our desired minus your estimated one. But just remember, this input, okay, this input collect all 60,000 different things, okay, all collect 6,000 different things. That means if you try to get the error, so this is n by k, this is a 60,000 by 100 matrix. This is also 60,000 by 100 matrix. So if you just subtract these two, you have error number 60,000 by 10. So actually this error contain all the errors from 60,000 times at all once. So that's the way you can update this one. But we have a little bit better efficient way to do it. When you update your weight, Okay, when you update the weight, you can just sum all the errors from 60,000 different data set at once and update the weight. That's the one way. Another way is that we can update the weight for a single training set. So right now our training set has 60,000. So maybe out of 60,000, one value come into your model and we get the error. Then we try to update the weight. Then we put the second training set and we update the weight and so on. I think that should be better than just get the error from 60,000 things at once and update the weight. Because we have too much data right now, maybe it's more efficient to update the weight per single training data set. Okay, that's why inside this for loop, we can make another for loop. I is equal to 1 to n training set. N training set is 60,000 data points. So we want to repeat the whole things, but inside a for loop, we try to go each individual training data and then compute everything and then update this one. Okay, so we just try to do the two end because we have two for loops here. And then in order to get the error now, because we just use a single data set, that's why in here I just put I and colon. So I means whenever I update I, only the single data set will be multiplied to my weights. Okay, that's why when you compare your final output, this one should be also I, comma, colon. So you want to look at the matched the output as a single data and then minus your estimated one. Okay, so that's why this one should be 1 by k. This is just a vector, and we got the error because we have a 10 node. Okay, so if you subtract your estimated from the y, then your error has a 10 number because we have 10 outputs. So we try to get the absolute of all the output and sum of them. Okay, so the sum of those 10 node errors, each node, we have a 10 node here. That's why when you compare your estimated value from your desired output, you have either positive or negative per each node. So we just absolute everything and then we just add them up. That will be the error one. Okay. So inside the for loop, we just repeat 60,000 times to update this weight, and then the epoch, the second, we just repeat again. So actually, we have so many repetitions to train the net. And then after you repeat the 60,000 times per single epoch, then I want to see my epoch error. So epoch error is epoch number is to some error. In this error, because if you repeat the 60,000 times, this error has 60,000 variable, right? So I want to add all 60,000 errors and then divide by the 60,000 times, so that my epoch error just shows the average errors per each single data set. So right now we define the error and epoch errors. So before we run the for loop, I want to empty my error here. So error, empty, and epoch error, empty. Okay, we are almost there. And then one thing more. Our X inputs, if you look at the X input, your X input is 0 and through the 125, right? But right now your output in the node, for different numbers, we just assign 1 or 0, right? So right now scale are too much different. And then when you initialize the weight, this weight value is some value between maybe -1 and 1, because we take the random number from standard deviations and divide with this number. Your weight value should be very low value, but your x is pretty big. So we try to scale down your x value as well. But I don't want to make 0 as a 0 number, because if you just plug a lot of 0 into your computations, the output is a lot of 0. So maybe we can try to avoid put the 0 into your node. So maybe we can slightly change the 0 to maybe a very small number. So we try to scale, okay, scale down your input to maybe from 0, 0, 1 through 1. So the best way to train down is you can just add 1 and divide by 256. I want to add 1 because I don't want to make my 0 to 0. So if you add 1, the 0 will be 1, and your other number should be just added by 1. And then if you divide by 256, then everything will be just scaled down between 0.01 through 1.0. Okay, almost 1.0. So we just scale down our x, and then we use it when you train your net. Then after that, after you train that, after we repeat 100 epochs, then I want to plot my epoch error, and I want to make sure that my error is kind of reducing as we repeat the epoch. X label should be epoch, and title should be change in error per single training data. And then after you train them, we have to save your weights because it takes a lot of time. So next time, if you quickly apply your test set, you need to store and reload those kind of weight, right? So let's save your weights. Maybe weight test met file, and then I want to save the matrix. This is a matrix for weights for single first layer, and then this is second weight. So we try to save these two weights matrix for next time to test it. So I think this is all code for training your sets. So we load it and we try to train it and so on. So let me save it, and then let's try to run. Okay. So I just I click the run button, and then right now we have some typo. So let me just check our typo here. So here should be the lambda and j. Okay. And then try to run again. I run, and let's wait because it takes a while. But in here I purposely omit the semicolon here. That means when the outer for loop is run, I see that how my error kind of changing it. Okay, so now this error number actually shows the result of this one. Whenever the one epoch kind of end, it just shows error. So it's good because error is kind of reducing it. So I know that eventually the error is getting minimized. That means I can convince that my weight is getting more optimized. So you just wait until it just end. Okay. So in slide I already put the code here, and then when I test my model, I used many different number of hidden layer. I just tried to use 300. I even tried a 1000 hidden layer. It took more than 5 hours to train my net. And as I said, we have a big for loop here. So this is epoch. The outer for loop is epoch repetitions. Inside is a 60,000 repetitions, 60,000 repetitions, because we want to run this computation for single data sets, okay? And then update this one for every single data set. So this is called SGD training. It's not batch training. We just take care of each single training set to update our weights. And then this is kind of results from my one-off testing results. When I tried to repeat my epoch up to 1000 epochs, I took about 90 minutes with a hidden layer number of 100. My error is getting reduced for sure. Okay, so when I look at this one, maybe 1000 epoch may not necessarily, maybe 500, even 300 should be enough to do that. And then this is kind of tests. So test results. I'm going to show how we test this one. So these are kind of scanned images from their mnist data sets. So they actually scan those kind of images and make images as a 20 by 28 pixels and get the grayscale informations. So when I test my trained data sets with these 10 numbers, then the success rate is about 90%. So the training sets recognize 0 as a 0, 1, 2, 3, 4, but they recognize this one as a 6. And otherwise, they correctly recognize all the numbers. My MATLAB code is still running. This one shows up to 41. My epoch is 100. So now try to your code, okay? Then try with your hidden layer as 100, and maybe increase your epoch maybe up to at least more than 250, and train your net, okay? And then come back to part 2 of video lectures, because in part 2 I will show you how we test these training sets.